All right, so today you're going to finish up the Fourier analysis on finite groups chapter, and and well, I don't remember what section. I think it's section 4. Uh, there is a nice application to graph theory. So without further ado, the first thing I have to do is define for you what a graph is. So graph for us, it will just mean a set V of vertices and a set E of unordered pairs of vertices. And these will be called edges. So here's the picture we're all probably familiar with. Suppose the vertices are 1, 2, 3, 4. Our edges might be something like 1, 2, 1, 3, 2, 4. And I haven't said anything about what are called loops. I haven't said that we can't have those. We can also have multiple edges, so I could stick another 1, 2 in here if I wanted. What would this look like? Well, let's put a dot for each vertex, label them 1, 2, 3, 4. So I have 2 edges from 1 to 2. I will mark those with lines from 1 to 2. I have an edge from 1 to 3. I have an edge from 2 to 4. And I have an edge from 3 to itself. So okay, so there's the picture that we're going to keep in our heads. Okay, so let gamma be a graph with vertex set V given by V1 through Vn and edge set E. We don't need to know what the things are, how the things are labeled in E. The adjacency matrix we will call it A, is given by Aij equals 1 if the edge Vi Vj is in the edge set and 0 otherwise. So in other words, if you look at your graph, if there's an edge between 2 points, well then the coefficient with indices given by those 2 vertices is going to be equal to 1, otherwise it's 0. So as an example for the graph that we have drawn here, the adjacency matrix is, so it's going to be 4 by 4 because there are 4 vertices. Is there an edge from 1 to 1? No. From 1 to 2? Yes. There's actually 2 of them, but all we care about is whether there is one. From 1 to 3? From 1 to 4? No. From 2 to 1? Yes. From 2 to 2? No. 2 to 3? No. 2 to 4? Yes. 3 to 1? Yes. 3 to 2? No. 3 to 3? Yes. 3 to 4? No. 4 to 1? No. 4 to 2? Yes. 4 to 3? No. 4 to 4? No. Okay, so this is the adjacency matrix for that particular graph. And notice that the adjacency matrix is, it's always going to be symmetric, right? Because the edges here are unordered. So if the edge 1, 2 is in the graph, and so is the edge 2, 1 because they're the same edge. So since this matrix is always symmetric, it's going to be diagonalizable, and that's by the spectral theorem, and the eigenvalues are going to be real. Okay, so speaking of eigenvalues, the set of eigenvalues of the adjacency matrix of a graph is given a particular name. It's called the spectrum of the graph. So if we had better notation, maybe we would write a little gamma here for the graph, but it's usually implicit, so I won't do that. Steinberg doesn't either. But just note that the spectrum does indeed depend on the graph because the adjacency matrix comes from the graph. Okay, so there is a whole area of graph theory called spectral graph theory, which is dedicated to studying graphs through their eigenvalues. What we're going to do today is study these eigenvalues somewhat and come up with a couple of nice theorems, not for general graphs, but for a particular case of graphs, which arise from groups. These are called Cayley graphs. Let me define what I mean by that. Let G be a finite group by a symmetric subset of the group G. What we mean is a subset S of G such that the following two properties hold. The identity is not contained in S, and S is in S implies that S inverse is in S. So of course this goes both ways, since if this property holds, then the opposite property has to also hold, because the inverse of the inverse is of course just S. So the Cayley graph of G with respect to S is the graph with, so the vertex set is going to be the group itself, and with an edge GH, so it connects G to H if GH inverse is in S. So this is equivalent to having HG inverse in S, right? Again, due to this unordered pairing for the definition of the edge. Okay. So in the literature, this word Cayley graph is usually used to mean the graph labeled by all the group elements with an edge connecting, I think, all of them. So this is a more refined definition here. Here's an example. Let's take G to be Z4 and S to be plus or minus 1 modulo 4, which is the same thing as 1 and 3 modulo 4. So what does this graph look like? what does the Cayley graph look like? Well, let's label our vertices 0, 1, 2, and 3, modulo 4. So the question is the difference inside this set? Well, 1 minus 0, sure. So there's an edge. 2 minus 0, no edge. 3 minus 0, no edge. 2 minus 1 is 1, there's an edge there. 3 minus 2 is 1, there's an edge there. And then 3 minus 0 is 3, there's an edge there. And it turns out that these are the only edges. So you can go through all the other cases if you like. And the adjacency matrix for this Cayley graph is 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. As another example, slightly more complicated, we could take G to be Z6, and we could take S to be 1, 2, 4, and 5 modulo 6. And we can label our vertices like so. 0, 1, 2, 3, 4, 5. And I won't go through all the every single edge, but I will draw it for you. So here are the edges that differ by 1. Modulo 6. Well, that one's 5, but and then we also have edges here and here, as well as, so 2 minus 0 is 2, that's in the set. We have an edge there then. 5 minus 1 is 4, we have an edge there. Uh, 5 minus 3 is 2, we have an edge here. And 4 minus 2 is 2, we have an edge there. And these are all the edges. Here's a nice graph. And I'm going to not write out the adjacency matrix because it's 6 by 6. Okay. So a Cayley graph of a cyclic group is called a circulant graph. In particular, this one's a circular graph on n vertices. And n by n circulant matrix is a matrix of the form A0, A1 through AN minus 1, and then you circulate AN minus 1, A0 through AN minus 2, and you keep doing this all the way down to A1, A2 through A0. So Steinberg says, and I have to admit I don't entirely understand the statement, but he says that an equivalent formulation for the circulant matrix is that there exists a function f from the cyclic group to the complex numbers such that aij is f of so the equivalence class of j minus the equivalence class of I. Okay. So if S is a symmetric subset of Zn, then the circulant matrix with F equal to delta S turns out to be the adjacency matrix of the Cayley graph of Zn with respect to S. Okay. So let's put that in perspective maybe. So if F is delta S, then Aij ooh, ooh. I see. Okay. So Aij will be exactly the definition that we had for the adjacency matrix before. That E there just turns out to be S. Okay. So what's our goal today? Describe the eigenvalues of the Cayley graph of an abelian group. Why an abelian group? Because they're simple. They're representations, or they're irreducible representations, are all one-dimensional, and that's going to allow us to do a lot of computations very easily. But a lot of this can indeed be extended to non-abelian groups. Okay, so first thing we need is a lemma. So let G be an abelian group. So G an abelian group. And let A be an element of the group algebra. So remember, these are the functions from G to C. Define the convolution operator from the group algebra to itself by A of B is the convolution of this A that we defined here with B. Well, what I won't check is that A is linear, just it's a straightforward computation. But we will check that chi is an eigenvector of A with eigenvalue the Fourier transform of A evaluated at chi. So remember, so this chi here is part of the dual group. So I should say for all chi in the dual group. So this chi is an element of the dual group, which is the group of irreducible representations of G. And the Fourier transform will act on that space. And a consequence of this is that A is a diagonalizable operator. So this convolution operator will be diagonalizable. Okay. Here's the proof. So again, I won't show linearity. It's just a straightforward computation. I want to check this eigenvector property. Let n equal the order of G, and let chi be in the dual group. And observe the Fourier transform of the convolution by the convolution theorem is just the product of the Fourier transforms. And we showed before that the Fourier transform of this irreducible representation chi is just n times delta chi. So let me just really quickly show that. So the Fourier transform of chi, well, it acts on the dual group. So I input another irreducible representation, and I get the order of G inner product of chi with theta. That's the definition of the Fourier transform on a finite group. And this was equal to the order of G if chi was equal to theta and 0 otherwise. And that's by the orthogonality relations that we derived. Okay, so this is delta chi. Right? This thing is going to act on the dual group space. And so it takes something like theta, right? And it's 1 if chi is theta, and then 0 otherwise. So this n here is to compensate for that order of G. Okay, so now this thing, when we plug in theta, is equal to, well, it's the Fourier transform of theta times n if chi is equal to theta, and it's 0 otherwise. And this is for any theta in the dual group. So what we have is that the Fourier transform of n delta chi is the Fourier transform evaluated at chi, which is now a number, times n delta chi. Okay, so now what we do is we go ahead and apply the inverse Fourier transform. Right, so the right-hand side is here, the left-hand side is up here. And what we find is that the convolution of A with chi is equal to the Fourier transform of A evaluated at chi, again, that's a constant, times chi, right? Inverse Fourier transform of n delta chi is it just goes back to chi. All right, so in other words, A chi, so the convolution operator applied to chi, is equal to this constant times chi. And so chi is an eigenvector of the convolution operator with eigenvalue Fourier transform of A evaluated at chi. And that's the thing we set out to prove. Okay. Now, for the consequence of this, that it's diagonalizable, it follows from the fact that this is an orthonormal set of eigenvectors for A. Why are they orthonormal? So that's, again, the orthonormality conditions that we derived for irreducible representations. Okay. So that proves the theorem. So lemma. And now here is a theorem. Let's let G be G1 through Gn. Let's let that be in a abelian group. And let S and G be a symmetric subset. So we'll let chi1 through chi-n be the irreducible characters. Of G. So remember that while there are equivalent irreducible representations, all of those irreducible representations have the same character if they're equivalent, right? So so there's a unique set of characters here that we deal with. Okay. And let A be the adjacency matrix of the Cayley graph. Okay, so all notation. We have an abelian group, we have a symmetric subset that allows us to produce a Cayley graph, and well, that group also has characters, or irreducible characters, and it has an adjacency matrix associated with the graph, right? And the way we describe the eigenvalues of this adjacency matrix, i.e. the spectrum of the graph, is like this. The eigenvalues of A are the real numbers lambda I is the sum over S and the symmetric subset of chi I evaluated at S. Moreover, the corresponding orthonormal basis of eigenvectors is given by the vectors vi is 1 over the square root of the order of g, chi I of g1 through chi I of gn. Okay, so given this setup, we have a group, we construct this Cayley graph, we construct this adjacency matrix. We want to know what the eigenvalues of the adjacency matrix are. Well, here they are, and moreover, the corresponding eigenvectors are here. And these are all given by the irreducible characters of the group. So here's how the representation theory plays a role. Okay, so let's go ahead and prove this. So I used A for the adjacency matrix, so let's define F to be the convolution operator here. We're going to define it by F of B equals delta S convoluted with B. So this S here is the entire symmetric subset, not just a particular element. By the lemma, the irreducible characters chi I are eigenvectors. Yes, eigenvectors of F with eigenvalues given by the Fourier transform of, so this was A before, right? And the eigenvalue was the Fourier transform of A applied to chi I. And this by definition is n inner product of delta S with chi I. And this is the sum over X and the symmetric subset of delta S of X chi I of X conjugated. And this is equal to the sum over S and the symmetric subset of chi I of S conjugated. Now, all of these representations, since we're assuming that the group is abelian, all of these irreducible representations will be one-dimensional, so they'll have degree 1. And so this conjugation will be the same thing as, well, effectively what it says is that these things are unitary. And so this will be the same thing as the sum over S and S of chi I of S inverse. And from here, we can just do a substitution, right? And we can rewrite this as the sum over S and S of chi I of S, which is exactly what we conjectured lambda I to be, the eigenvalue. Okay. So it follows that if B is a basis delta G1 through delta Gn for the group algebra, then the matrix, which I'll denote by FB to distinguish it from the linear map F. So this is the matrix with respect to the basis B. This thing has eigenvalues lambda 1 through lambda n, and it has eigenvectors v1 through vn, so given by where did you go? Here we go. Given by these vi here. Okay, so papers flying everywhere. All right. Moreover, these vi are orthogonal. And this follows from the fact that the chi I are orthogonal. So what's left? It remains to be shown that A is the adjacency matrix is actually equal to the matrix for the convolution operator that we defined. So if we apply this convolution operator to delta Gj, this is delta S convoluted with delta Gj, and this is equal to the sum over S and S of delta little s convoluted with delta Gj. So this is just because the delta function on an entire set is just the sum over the delta functions for each individual element in the set. And this is equal to the sum over S in S of delta S G J. This is something we proved, I think, last time. So one of the nice things about the convolution operator is that it has this property on the delta functions, which form a basis for our group algebra. Okay, so by recalling that the ij coefficient of this matrix, or sorry, the ij entry is the coefficient of delta gi in f of delta gj, we conclude that this coefficient is equal to 1 if gi is equal to sgj for some s in our symmetric subset and 0 otherwise. Okay, so that comes from right here. And then we can rewrite this as 1 if gi gj inverse is contained in S and 0 otherwise. But this is exactly the definition of the adjacency matrix of the Cayley graph. Okay, so we do still need to verify that the lambda I are real. So if S is contained in the symmetric subset, then S is equal to S inverse, or it's not. In this case, chi I of S is equal to chi I of S inverse. And so this is equal to chi I of S complex conjugate. And so chi I of S must be real. And this is what we said the eigenvalue was. So the eigenvalue is real. So in the other case, so for S not equal to S inverse, so remember this is still an S, then what we have is that chi of S plus chi of S inverse is chi of S plus chi of S complex conjugate. And this thing is real. And it follows that the eigenvalue, which is sum over S in S of chi I of S, will be real. So remember the definition of the symmetric subset assumed that if S was in S, then the inverse was also contained in that symmetric subset. So for every S in here, you do have the pair. Okay. Unless, of course, S is equal to S inverse, in which case it's real anyway. All right. Anyway, so the point is that this whole thing is real, and that's the end of the proof. Okay, so that is a nice application of representation theory, or at least character theory, to the theory of Cayley graphs. And a corollary of this is if A is a circulant matrix of degree n, which is the adjacency matrix of the Cayley graph of Zn with respect to the symmetric subset S, then the eigenvalues of A are lambda k. So because the group is cyclic, we know what the irreducible representations are. They're given by the roots of unity, essentially. And the eigenvalues are the sums of these irreducible representations. how do I say this? It's the sum over the elements of the symmetric subset. So in this case, it'll be equivalence classes of elements of Zn of the individual irreducible representations evaluated at those n. It's either 2 pi I k m over n. So the k here is indexing which irreducible representation. So here k runs from 0 to n minus 1. And a corresponding basis of orthonormal eigenvectors is given by v0 through vn minus 1, where vk is 1 over the square root of n. And I'm going to write this as a row vector, 1 e to the 4 pi I k over n, all the way up to e to the 2 pi I k n minus 1 over n. And I'll put a transpose there. That is a transpose. Okay, so it's just the theorem, but applied to circular matrices. Right, so if you ever have a matrix that has that nice form, well, then you immediately know its eigenvalues and eigenvectors. Okay, so again, this approach can be generalized to non-abelian groups, with the caveat that you need the symmetric subset S to be closed under conjugation. So that was the key property in a lot of these calculations. So if you want to go to the non-abelian case, you need S closed under conjugation. Okay, so that concludes the application to graph theory. But speaking of non-abelian groups, remember when we did Fourier analysis last time, we only did it for abelian groups. So what does this look like for non-abelian groups? Well, for a non-abelian group G, we have that the group algebra is no longer equal to the center of the group algebra. So all the elements of the group algebra no longer commute with each other. So this means that L of G is a non-commutative algebra. So a consequence of this is that we can't find a Fourier transform that turns convolution into a pointwise multiplication, because that pointwise multiplication itself is commutative. So we don't have a convolution theorem, and that's something that we would really like. So instead, what we'll do is we'll try to replace pointwise multiplication by matrix multiplication. And so we'll sort of, well, you'll see. We're basically going to upgrade copies of C into matrix algebras. Okay, so first let's recast the abelian case in a different form, and then it'll become clear how to extend it. So let's go back to the abelian case. If G is finite and abelian, with irreducible characters, let's call them chi1 through chi-n again. Then to each function, call it f. So each element of the group algebra, we can associate its vector of Fourier coefficients. So we have this nice theory of Fourier analysis for abelian groups, and we can arrange the Fourier coefficients into a vector. So what we mean is we can define a T, which takes an element of the group algebra and sends it to a vector in Cn. And the way we define it is T applied to F is equal to, well, it's the Fourier coefficients. So remember, those are in F inner product with chi1 through in F inner product with chi-n. So these are the Fourier coefficients. So the Fourier inversion theorem will actually tell us that T is in fact injective. So T is injective by Fourier inversion. You can also show that T is linear. I'm not going to do the calculation, it's pretty simple. But the point is that since the dimension of both spaces are the same, it follows that T is an isomorphism. Yes, I should say this is an isomorphism of vector spaces. Okay, in fact, it's actually an isomorphism of algebras, and the way you see that is as follows. So if you take, if you apply T to a convolution of A with B, well, then this is equal to the Fourier coefficients of the convolution. And then we invoke the convolution theorem. This is Fourier transform of A, Fourier transform of B, evaluated at chi1. Maybe I'll just go ahead and skip a step and write the chi1 in here. Okay. And we can write this as the pointwise multiplication of two vectors. And finally, we recognize this as T applied to A times T applied to B. Okay, so this shows that the algebra structure is respected, and so we have an algebra isomorphism. So at least for finite abelian groups, we have that L of G is, so the group algebra is isomorphic as an algebra to Cn, which of course itself is just n copies of C. And now the idea is that this direct product form is kind of showing, well, it's kind of reflecting the fact that the irreducible representations of G, which is abelian, are all degree 1. So for non-abelian groups, we might conjecture that we should be able to replace C with some matrix algebra and define a Fourier transform that is nice. So that's exactly what we're going to do. Let G be a finite group. Non-abelian, abelian, doesn't matter. And let's give it order n. And we're going to have the phi1 through phi s, as usual, be a complete set of unitary representations. Maybe I'll write down exactly what I mean. A complete set of unitary representatives, actually, representatives of the equivalence classes of irreducible representations of G. So again, G has several irreducible representations, and there are some that are equivalent to each other. And so we mod out by the equivalence relation, which identifies the representations that are equivalent, and we're left with several equivalence classes. Each of those equivalence classes has the same character, okay, because the character is a class function. But the point is just that we choose some representatives, one from each of those equivalence classes. Okay, so as usual, we will have dk denote the degree of the kth irreducible representation, and the matrix coefficients will again be denoted phi ijk from G to C, and are given by phi gk is phi ijk of G. So these phi ij's are the coefficients of the matrix of phi k's. Okay, and one more thing. So we also showed that if we normalize these things with the square root of dk, then these form an orthonormal basis. For the group algebra. Okay, so this is all stuff from the past. All right, now how do I define my Fourier transform? Like so. So we define T from the group algebra to several matrix algebras. That should be a C. I think I want to do S. So we lift these copies of C to copies of MDI of C. So copies of the matrix algebras. So if DI happens to be 1, then we're just left with a copy of C. So this is indeed a generalization. How do we define this? Well, we define it by T acts on F in the following way. So T is the vector of Fourier coefficients, but we don't yet know what this means because these representations here aren't necessarily one-dimensional. So we're still not in the regime of abelian groups. However, the coefficients of this representation are. So the way we define this is by saying that its ijth entry is equal to n times, well, the usual definition that we have been working with. And so this comes out to be the sum over G and G of f of G times phi ij of G k complex conjugate. Okay, so how do we extend to the non-abelian case where the representations are not necessarily one-dimensional? Well, we work with the entries of the representation instead. All right. So we call this TF thing the Fourier transform of F. So more succinct notation for this would be the Fourier transform of f applied to phi k. So remember, this is going to be a matrix, is equal to the sum over g and g of f of g phi g k complex conjugate. Okay, so this is the more succinct notation. So a Fourier inversion theorem does still hold. We let f be in the group algebra, then f can be written as sum, or sorry, 1 over the order of g sum over ijk of dk Fourier transform of f evaluated at phi k, the ij coefficient phi ij k. Here's the proof. We know that f is the sum over ijk of f inner product with square root dk phi ij k, because these things form an orthonormal basis for the group algebra, an element of which f is. Okay, oh, sorry, I missed my dk phi ijk here. These are just the coefficients. Okay, so this is equal to 1 over the order of g sum over ijk of dk order of g inner product like so. And this thing here we recognize as the Fourier transform. J phi ij k. And that's exactly what we wanted to show. Okay. So another property we would like to have is for the map T to be an algebra isomorphism. And well, the first proposition I have for you says that it's in fact a vector space isomorphism, which is not quite what we want, but it's a good start. This is a vector space isomorphism. Okay, so linearity, well, I'll go ahead and do it, why not? Here's the proof. If we take a linear combination of, oops, that should be a 1, yeah, of elements of the group algebra, and we take the Fourier transform at phi k, this is equal to the sum over g and g of c1 f1 plus c2 f2 evaluated at g phi g k bar. But this is equal to c1. So this is the definition of Fourier transform. I've skipped a step here where we write it as the order of g times the inner product. And this is just the inner product. Right? And then there's a 1 over the order of g that was canceled. This is the sum over g and g of f1 of g by gk bar plus c2 sum over g and g of f2 of g by gk bar, and that is just C1 Fourier transform at phi k plus C2 Fourier transform of f2 at phi k. Okay, so that gives us linearity. So the Fourier inversion will again give us injectivity. And since the dimension of the group algebra is the order of G, which is the sum of the squares of the degrees of the irreducible representations, well, this will be equal to the dimension of that product. So we have injectivity, and the dimensions are the same, and so this must be an isomorphism. So P is a vector space isomorphism. Okay. So last thing I want to show today is that this is in fact an algebra isomorphism. What I should have prepared today was the fact that the convolution theorem still holds, but I did not. It slipped my mind. In fact, Steinberg doesn't even do it. It just says that it's true. But maybe that's a good project if anybody's interested. Okay, but the Fourier transform T from L of G to MD1 of C through MDS of C is an isomorphism of algebras. We already showed that it was an isomorphism of vector spaces. So all that's left is showing that it respects the algebra structure. So it suffices to show that T of the convolution is in fact equal to no wait, this is my convolution theorem. Okay, we've essentially got to prove the convolution theorem to prove this is an algebra. Okay, all right, great. So actually, we don't even need to do things this general. It suffices to show that the Fourier transform of the convolution of A with B evaluated at phi k is this guy, the product of the Fourier transforms. Okay. So essentially just evaluate at the irreducible representations. How do we get this result? Well, start from the left, and we'll unpack the definition. This is the sum over x and g of the convolution of A with B evaluated at x times phi x. Why do I have an x here? Okay, I've written some bad notes. Give me one moment. There should be two indices there. No. Okay, great. Yeah, no, this is the representation evaluated at x. Sorry, I was thinking of the entries of the matrix, but that's not the case here. We're evaluating this representation at X. I forget about Steinberg's notation. Okay, great. So this is the sum over X and G of phi X K complex conjugate. And now I unpack the definition of the convolution. Sum over Y and G of A of X, Y inverse, B of Y. Okay, let's keep going. I will swap the order of the summations. A, X, Y inverse, phi X, K bar. And now I can rewrite that inner sum using a substitution. So we substitute Z equals X, Y inverse, and we do the whole thing. X ranges over G, and so Z also ranges over G. So we're allowed to put a Z here. And what am I missing? This should be a phi Z Y K. So this is evaluation at ZY, not the entry. And then this is equal to the sum over Y and G of B of Y, sum over Z and G, A of Z, and then this is a homomorphism. And so we're allowed to split this up into a product. All representations are homomorphisms. And now we swap the products, or sorry, not the products, we swap the sums again. Maybe, well, I mean, I do swap the sums, but you don't really need to, I guess. You could just pull this phi yk over here. And missing a sum over Y and G of B of Y, phi Y, K complex conjugate. And this is the Fourier transform of A at phi K times the Fourier transform of B at phi K. And so that proves the convolution theorem, and therefore shows that this Fourier transform is an algebra isomorphism between the group algebra and this product of matrices. Okay, great. Yes, I'm glad that convolution theorem showed up. Any questions?
Oh, no.